Thank you.
Okay, we probably have time for just one quick question if anybody has them. Otherwise, maybe they would have to be offline and we can move on to Surya's talk. Any questions for Francesco? Okay, thank you once again, Francesco. And Surya, are you ready to go?
Yeah, I think so. Let's see. Okay, great. Okay, can everybody hear me and see my slides?
We're good to go.
Okay, great. So thanks for inviting me here. I wouldn't say that I'm necessarily an insider in the stochastic thermodynamics community, but I have actually admired this community from afar and also up close because I think some of the most beautiful and elegant results in physics have actually come from this community. So I'm a big fan. So I'm quite honored to be invited to speak here. So I'm going to talk about universal energy accuracy trade-offs in non-equilibrium cellular sensing. And so that's the subject of this paper, and I'll spend the bulk of my talk discussing this paper. But at the very end, I'll advertise two other papers that have to do with stochastic thermodynamics in very different settings, in deep learning and in diffusion models. And I'll just be advertising those works. Okay, so let's get started with the bulk of the talk. This is joint work with Sarah Harvey and Shubhani Lerviri, a student and postdoc of mine. Okay, the motivation is bacterial chemotaxis. So a fundamental goal of bacteria is to move to locations with higher nutrient concentrations. So how does it do this? It's only about 1 micrometer big, so it can't measure the spatial gradient of the concentration between its head and its tail. It uses a different strategy. It senses the time derivative of external nutrient concentrations as it moves, and if this time derivative is increasing, it will reduce its rate of turning and tend to go straight as long as things are getting better. But if the time derivative is decreasing or constant, it will increase its rate of turning and search for different directions. And this allows it over time to move to regions with higher nutrient concentration. So a critical question is, how does it sense concentration to begin with, even at a single location and time? So it's done by cell surface receptors that bind the molecules of the nutrient. And once the cell surface receptor is bound, it creates internal signaling molecules that signal the presence of the nutrient, and it detects the concentration in this manner. So a very simple model of such a receptor is a two-state receptor, with a state 0 for unbound and a state 1 for bound. And the transition rate from unbound to bound must depend on the concentration of the nutrient, C. And then the unbinding rate might be concentration independent. So this receptor will undergo some stochastic trajectory over time, alternating between unbound and bound. And so you have this kind of communication channel from the external concentration to a two-state receptor to a stochastic trajectory. And you'd like from the stochastic trajectory to construct an estimate of concentration, right? And there's a very classic result from Berg and Purcell. I'm sure many of you are familiar with it, where if the concentration estimate is based on a simple observer that in a very biologically plausible manner just measures the fraction of time the receptor is bound, just measures the fraction of time the receptor is bound, then the fractional estimation error of this estimator, the variance and the error of the estimator divided by the mean squared the true concentration, is 2 over n bar, where n bar is the mean number of binding events in time t, and capital T is the duration of the stochastic trajectory. So this was thought for a long time to be a fundamental limit on how well we can estimate concentrations using a simple receptor. But is it really fundamental? And if not, how can we evade it? Well, if you think about the derivation, there are two key assumptions. One is that we're using a simple observer to do the estimate. The entire complex stochastic trajectory is reduced by the simple observer to one statistic, the fraction of time bound, and the estimates performed based on that. The second is that we're not using a more complicated multi-state receptor that's operating at non-equilibrium and therefore spending energy, right? So we could try to evade it by breaking these assumptions. One assumption might be to go to an ideal observer. Is there a better way to convert the entire stochastic trajectory into a concentration estimate? And what would actually be the best possible ideal observer? What would they do and how well would it perform? Then the second is going to multi-state non-equilibrium receptors, and the questions we'll ask are, if these receptors consume energy, does it yield improved performance? Can this improved performance be attained even with a simple observer now? And what are fundamental performance limits given an energy and time budget over the space of all possible receptors? Right? So that's what we'd like to ask. So this first part was done in a very nice paper by Ned Wingreen and company. And so they noted that, of course, the ideal observer is just the maximum likelihood estimator. So if you have the entire stochastic trajectory as an observed quantity, x of t, you compute the log probability of that observed trajectory if the concentration had been C, and you compute the most likely concentration, and that's your estimate, right? And so this uses the stochastic trajectory, and the fractional error of this estimator is actually 1 over n bar. Right, and the difference between the 2 over n bar here and the 1 over n bar here can be understood heuristically as follows, based on what the ideal observer does. So the ideal observer measures the mean duration of unbound intervals in time t. So how long has the receptor been unbound? And this makes a lot more sense because the transition rate out of the unbound state from 0 to 1 depends on the concentration, but the transition rate out of the bound state is independent of concentration. So the former is signal and the latter is noise. Of course, they're related because they sum to capital T, but it's actually better to concentrate on the unbound duration and ignore the bound durations. Okay, that's one way to understand this estimator. Okay, but now you could ask, how does this generalize to much more complex receptors that are not two-state systems, but have an arbitrary kind of Markov process where some of the transitions depend on concentration, right? How much information does the stochastic trajectory contain about the concentration? So we're going to look at receptors that are Markov chains, continuous time Markov chains, and the states can be partitioned into a set of non-signaling states that are unbound and signaling states that are bound, right? And so as a function of the number of states, the observation time, and the degree of energy consumption, how well does the ideal observer do, and what computation on the trajectory must it perform? And also, how well does the simple observer do, and what is the best achievable performance over all possible receptors? So first, let's take care of the ideal observer. So first of all, what does the ideal observer do? So we generalized Wingreen's result to this case, and you get a much more complicated computation. So what the ideal observer does is it computes certain statistics of the stochastic trajectory, and we'll build them up one by one. So the first is if you have a single stochastic trajectory of duration capital T, you can compute the empirical density, which is just the fraction of time spent in state I on that particular trajectory, right? You can also compute the empirical transition rates from states I to J, which is just the number of transitions from state I to J on that trajectory divided by capital T. These are random variables and they inherit their stochasticity from the stochasticity of the trajectory itself. From this, you can construct the empirical binding rate, which is the sum of the transition rates from every signaling state, from every non-signaling state to every signaling state. And you can compute the expected binding rate, assuming you had the empirical empirical density and the true transition rates, Qij. And then the ratio of the empirical binding rate to the expected binding rate is the optimal estimate of the concentration. So it kind of makes sense. The higher the concentration, the higher your binding rate. And this is the normalization factor. Okay, so the ideal observer computation is quite complicated and likely biologically implausible. But we can first ask how well does it do? And we get a very simple result. It actually does the same. The ideal observer on any complicated receptor performs just as well as it would on this very simple two-state receptor. Again, if it has access to these complex statistics of the stochastic trajectory. So the error is actually the same. So spending energy doesn't help you at all if you have an extremely sophisticated ideal observer operating downstream. But cells likely don't have that ideal observer. They likely have something more like a simple observer. So now let's go to non-equilibrium receptors with a simple observer. Okay. So for the simple observer, the estimate C is based on just a single statistic of the stochastic trajectory, which is just the empirical fraction of time spent in the set of bound states. Okay. For large T, this random variable obeys a large deviation principle. The probability distribution of the fraction of time spent in the bound states uh, goes like e to the minus t times this large deviation rate function, I of qt. We're skipping a lot of mathematical steps here, but what we did is we found an upper bound on the large deviation rate function, and then this yields a lower bound on the variance of the fraction of time spent. And this is that lower bound, actually. And you can think of this as a particular thermodynamic uncertainty relation for the fraction of time any stochastic process spends in any set of pooled states. So this is a very general result that doesn't depend on this partition. You just take any Markov chain, continuous time Markov process, you partition it into any two set of states, pick one set of states and asks, what's the variance of the time spent in that set of states under a finite time trajectory of duration capital T? And you have the entropy production here, which measures the irreversibility of the process. And you have the mean number of transitions from the unbound to the bound, or one set to the other set. Okay. And so now you'll notice if the entropy production goes to zero, oh, sorry, that's for later. Okay, so this is actually a general result that might be of interest in general beyond just cellular sensing. And so what this says is that entropy must be produced or energy must be consumed to reduce the variance of the time spent in a set of pooled states. Okay, now with that result in hand, we can go back to the actual estimation error, which depends on the fluctuations in the amount of time spent in the bound states. And the estimation error can be then lower bounded as follows, as 8 over T times the entropy production plus 4 times the mean number of binding events. And you'll notice when the entropy production goes to 0, this reduces to 2 over n bar. So it generalizes the classic Berg-Purcell result to a situation where you're a non-equilibrium. Okay. So it's tight when the entropy production is small, but it turns out, of course, to be vacuous when the entropy production is large, because then it's just saying the error is bigger than zero. But remember, when the entropy production is, there's another bound that we have based on this Kramer-Rao bound for the ideal observer, which basically, based on the idea that no simple observer can ever do better than the ideal observer, and the ideal observer does 1 over n bar, we know that there's a second bound that takes over when this becomes vacuous. So a simple observer's error must always be bigger than 1 over n bar. Okay, we can go beyond these bounds and we can actually exactly compute the estimation error in terms of first passage times. Okay, so we obtain a simple formula in the case of one non-signaling state. We obtain also a more complex formula if there are more non-signaling states. And the formula is actually quite simple. The estimation error is 2 over n bar times the unbinding time over the holding time. Now, what are these two times? So T hold is the mean first passage time from any signaling state to the non-signaling states, conditioned on the fact that you just entered the signaling states, right? So that you can think of this as the mean duration of a single journey through the bound states or signaling states from start to finish of that journey. Okay. What's T unbind? T unbind is the mean first passage time from a bound or signaling state to the non-signaling state, just conditioned on the fact that you happen to be in the signaling state currently, not conditioning on the fact that you just entered the signaling state. So this is the mean time to unbind given the receptor is currently bound, regardless of when it entered the bound state in the past. Okay, of course, for the two-state receptor, the unbinding process is memoryless. So T hold and T unbound are the same, right? So then this cancels and you recover Berg-Purcell, right? So you can think of this as a far-reaching generalization of the classic Berg-Purcell result to arbitrary bound state kinetics here. So arbitrary transition rates between the non-signaling and signaling states, or unbound and bound states. Okay, so what good is this formula? Well, these first passage times depend on the transition rates, and we know analytically how they depend on it. And then we can take gradients of the first passage times with respect to the transition rates. So then we can get analytic formulas for those gradients. So now we can numerically optimize over the space of transition rates of any Markov chain, the estimation error, and even do a constrained optimization or minimization of the estimation error over transition rates subject to a given energy budget, right? So then we can actually numerically compute a period optimal trade-off between error and energy. And that's what's on this slide. So there's a lot on here. So let's unpack this slowly. Okay, so this axis is the energy consumed per binding event, okay, in units of kT. So more energy here, less energy here. This axis is the fractional estimation error times the number of mean binding events, right? So when you divide by so this point here is Berg per cell. At zero energy consumption, the coefficient of the error is 2, right? This black curve is our large deviation theory lower bound on the estimation error at any given entropy production, and it becomes vacuous around here. This horizontal line is our lower bound on the estimation error given the ideal observer. Okay, so these are lower bounds, and this is a provable forbidden region in the error energy space where no receptor can ever enter that forbidden region, right? These are the results that we obtained from numerical optimization. So what we did is we numerically optimized the estimation error at every possible energy consumption, and we never found a receptor with any number of non-signaling states lower than this curve. So this is a numerically computed Pareto frontier, and we can characterize it a little bit better. First of all, one non-signaling state is sufficient to minimize error at any budget. Okay. At higher energy, you need more states to achieve this Pareto optimality. So these numbers tell you the minimal number of states required to achieve Pareto optimality, and the minimal number of states increases as you increase your energy budget. Second, ring topologies, so receptors with just a pure ring topology are sufficient but not necessary to achieve Pareto optimality at low energy consumption. But at high energy consumption, everything that we found were rings. Now, a very simple receptor topology to analyze is just a receptor that goes through a ring, say, of conformational states as it gets bound, with just uniform transition rates. So there's a forward rate and a backward rate, and the degree to which they're different is the degree to which entropy is produced or energy is consumed. And it turns out that these rings with uniform transition rates are close to Pareto optimal as long as the size of the ring matches the energy budget. So for example, each of these curves are uniform rings of different sizes, and very large rings that don't spend any energy are terrible, but they become very good and close to Pareto optimal as long as, again, the size matches the energy consumption. So to get over here, you need to use a larger ring and spend more energy. Okay, and we can come up with an analytic formula for the error and the energy consumption of these uniform rings. So basically, the take-home message is uniform rings of increasing size and energy are approximately Pareto optimal. And what's very interesting is that the Pareto optimal frontier gets very close to 1 over n and asymptotically approaches it, actually. So this tells you that a simple observer, a biologically plausible simple observer, observing a large energy-consuming ring can match the ideal observer of a two-state receptor. Okay, so this is how you get to the fundamental limits, and of course, information theoretically, nothing can do better than the ideal observer on a two-state receptor. Okay, so that kind of takes care of the take-home messages of this paper. Now, these will be much shorter, and I'll just give you very high-level uh, take-home messages to whet your appetite. I think these will be of interest to the community because of the way we use stochastic dynamics. And it's all published. You can look at the papers. So this is the paper that I'll discuss, again, with very talented grad students, Feng, Daniel, and Atsushi. Actually, ironically, all three of them are graduating this quarter. I have 9 defenses that I have to go to in May and June. These are 3 of them, and they're all going on to great jobs next. Okay, so here's the take-home messages. So let's say you're training a neural network, okay? You're optimizing over weight space and you're trying to minimize the error. This is the training error landscape. It's extremely complicated. It's riddled with saddle points, many local minima, and so forth. You start at high error at a random point in weight space, and you do stochastic gradient descent. So you're doing gradient descent on the training error landscape But each time you take a gradient step, you're not computing the gradients with respect to every single example. You're computing the gradients with respect to a subset of examples called a mini batch. And then each step you take a different mini batch. The random choice of mini batch introduces stochasticity. So you have this stochastic energy descending dynamics, okay? Oftentimes, many people try to model this using a Langevin model, but then they don't choose the noise correctly. They usually choose a noise that's just isotropic and not dependent on where you are in weight space. But the noise is really corresponds to the covariance of the gradients across mini batches. And that depends on where you are in weight space. So the key insight of this paper is that any accurate Langevin model of stochastic gradient descent in machine learning must include a position-dependent diffusion tensor, where the dependence comes from the covariance of gradients, and that depends on where you are in weight space. We computed this position-dependent tensor, and we showed that it vanishes at saddle points in the training error landscape, corresponding to points of enhanced symmetry where many, many neurons have identical incoming and outgoing weights. So these are saddle points because you can always get to lower training error by specializing the neurons that are identical and doing the symmetry breaking. But because the diffusion tensor and the drift vanish at these saddle points, the dynamics stochastically gets attracted to these saddle points and doesn't get to the minima. This is actually a good thing because if it were to get to the minima, it would overfit to the training data and you'd have worse test error. These saddle points, even though they're higher in training error, they have lower test error on new examples. So this is actually a good thing. The position-dependent diffusion tensor, which vanishes at points of enhanced symmetry, greatly reduce the number of effective degrees of freedom that deep learning has access to, prevent overfitting, and you end up at a saddle point. And we actually showed both the theory and numerical simulations in real deep networks to show that this is happening. Okay, so I'll just leave that at there. And then some of the most recent work we've done is this analytic theory of creativity in convolutional diffusion models. Again, I'll just give you an advertisement. This is work again done with a younger grad student, Mason, and it's going to appear in ICML this year. So these diffusion models create endless amounts of creative new images, right? How are they doing that? Okay. So the main idea behind diffusion models is that you take data, examples of data, and you noise them up by having them diffuse in image space until they become white noise. And then you take a neural network and you train it to reverse this destruction of structure. And if that works, you should be able to sample noise, feed it into your neural network, and generate an image. Interestingly, for this community, this was directly inspired by the proofs of fluctuation theorems that look at log probability ratios of forward versus reverse trajectories. When we came up with this diffusion model, I encouraged my group to study stochastic thermodynamics because I was interested in it. So we are doing a reading group on it. We were looking at these log probability ratios of forward versus reverse trajectories. And Joshua had the brilliant idea of why do we make the reverse trajectory just be the reverse of the forward trajectory? Why couldn't we replace it with a neural network and then try to optimize, make it as reversible as possible? And he got it to work, and that led to this paper. So I don't know if this folklore has reached this community or not, but it's safe to say that the birth of generative AI, at least in the form of diffusion models, really was born from the field of stochastic thermodynamics. Feel free to share that kind of story with your students and stuff. And of course, we put the word nonequilibrium thermodynamics into our paper. This was the first diffusion model paper. Didn't quite stick though, unfortunately. So that's our bad. Anyways, okay, but here's now a puzzle. If it's perfectly reversing the diffusion process, how can it generate new images that are not like any of the training set images? i.e., how is it creative? And the key idea is that the neural networks that do this reverse diffusion are these convolutional networks that obey two limiting principles. One is locality, as it's reversing, the decisions that each pixel makes depends only on its neighbors, and the other is equivariance. The decision rule used by a pixel here is the same as the decision rule used by a pixel here. So what we can do is we can analytically write down the optimal local equivariant reverse diffusion process, and we get an analytic process where each local patch of the image undergoes reverse diffusion to become some training set patch of some training set image. and another patch independently undergoes reverse diffusion to become some training set patch of a different training set image, and it builds up a local patch mosaic of the training set. So we compared our analytic theory to actually trained diffusion models, and we got a beautiful quantitative match. What you're seeing here is on the right side of each pair of pictures, you take some noise and you feed it into a trained diffusion model. On the left side, you take the same identical noise realization and you feed it into our analytic theory, and then we get a prediction for what the trained model would predict, and you see a beautiful match here with a very high R squared. So there's lots of details. I'll leave it for the paper and I will stop here. And these are the three things that I covered. Thanks.
All right.